So guys, we've been talking for the last week or so all about KMT, kinetic molecular theory. We've done the math on it. We've done thermochemistry and calorimetry. Now we're going to talk about a little bit more of the why behind what we see with KMT. We're going to talk about intermolecular forces today. Why do some substances exist as gases at room temperature, some as liquids, and some as solids? Right? The answer to this question is IMFs, okay? So there's two kinds of forces. We've talked about one of these kinds already this year. So these, for the most part, these notes, guys, go right along with this worksheet. There might be some gaps in there, and I apologize, so we can add some things in there if you need to. But just kind of, it'll kind of roll right along with it. All right, so two types of forces. You will want to, right below this, we have it. It's kind of two big categories of the forces that we need to be aware of. All right, between separate molecules. That's kind of what we're going to be looking at. So intramolecular forces, the key word, guys, or the prefix there, intra, is within a molecule. We've talked about this back in Unit 4. What are the three types of forces that we discussed in bonding? Yeah, they're up there right on the slide. So those are the three intramolecular forces. So within a molecule. So that's like when you have an intrastate highway, it's like within New York State alone, where the interstate goes, like we said last week, between states. I-90, it stretches from, New York all the way to, I know at least Chicago, I believe, and probably even further. I know I-40 goes from California all the way to the East Coast. It goes coast to coast within it. So intra is within. And those bonding forces, like we said, ionic, metallic, and covalent in no particular order. Okay, review for us. So we're not going to talk about these ones with bonding. We've already done that. Now we're just going to talk about the forces that hold different particles together that have already been bonded. Okay, different molecules and things like that. So intermolecular forces, between or among. So between different molecules. These are weaker than intramolecular forces. So intermolecular forces, guys, they are weaker. Okay, think about it. What's happening with intramolecular forces? They're either donating, sharing, or kind of moving what? What's driving bonding, those intramolecular forces? Electrons, right? Transfer or sharing of electrons. So when we talk about intermolecular forces, guys, the electrons have already been shared or transferred from one atom to another. So you have your molecule set. So for example, and you don't have to jot this down, we've got water molecules. All right. So you have this piece already put together. And I know it's a little bit difficult to see, and I apologize for that. So then we're talking about the force between two water molecules. All right? There's no transfer of electrons because the molecules are already stable because of that transfer or that sharing that's taken place. So we are just looking at, okay, well, how do these species interact with one another? And that's what we're going to get into, is how do two molecules kind of coexist or interact to make up what we actually see. Because can we see one molecule or one atom, guys? No, we see a mole or 2 moles of atoms or molecules. So they've got to be interacting somehow for something like water to have the properties that we've talked about over the last week. We good? Okay. So guys, intermolecular forces, they are the things that determine the phase. And this isn't probably brand new to us or shocking because we've been looking at this for the last week and a half or so. But the competition, guys, is between the strength of the intermolecular forces and the kinetic energy, which, again, we've talked about. So we're kind of getting back into the why behind certain pieces. So where you see where it says competition in your notes, this first part's all I want you to kind of write there. Okay? The other part is just kind of setting us up for other pieces. So you copying down, only copy down that competition piece. We will get into strong IMFs and weak IMFs in just a minute. Okay? So forces, guys, if intermolecular forces are strong, the substance is going to be a solid or liquid. Does that make sense to us? Absolutely, because if forces are strong between particles, what aren't the particles doing?
Do we write boundaries?
Nope, I'm just asking a question. If the forces, guys, holding particles together, if they're strong, what aren't the particles able to do? Move or spread out or flow, right? They're not going to spread out because those forces are holding them together, right? The example I think of is when you have, maybe this was you when you were a kid, if you have like a 3 or 4-year-old in a store, they're going to want to run around and see everything, right? Did anybody ever have a leash when you were a child? I think maybe I've talked about this already because I, for some reason, was thinking Tony. I feel like we've already talked about this, right? Right. So going back to that idea, like there's some kids that you've seen that just go crazy and run off, and parents can't keep track of them. So the parents want to have some type of ability to keep them close, whether that's one of those backpack leashes or the wrist things. I think I had one of those. What's that? It could never, right. So you had a lot of energy. The more energy you have, you broke that bond between your parent or that leash or whatever it is. Guys, that's the same thing that's happening with intermolecular forces. Stronger they are, they're going to hold them together more, but they can only hold them together so much because the kinetic energy can change. What does kinetic energy, guys? What measures kinetic energy? Temperature. There it is. Temperature. Okay? So if the temperature gets higher, they get more kinetic energy, they can start moving faster. And the opposite, guys, is true as well. If the forces are weak, they're going to be a gas at room temperature. They're going to spread out and go crazy. So, it's a balancing act. You do not have to write any of this down. This is just kind of showing you a kind of more of a visual, kind of the balance between the two. So you've got your intermolecular forces and kinetic energy, guys. So in this example, kinetic energy is higher than your intermolecular forces. Therefore, it's going to be a gas at room temperature because they can overcome those forces that are trying to keep them close together and they can spread out. All right? Should make sense to us. Again, we've looked at this in depth already. Where if the kinetic energy is lower than those forces, it's going to be more of a condensed phase. Now, condensed, guys, it could be a solid or a liquid. What's the other factor besides temperature that determines the phase? Pressure, okay? And what is pressure again? Collisions, yeah. I like it. You guys are doing it with your hands because that's a visual to help you remember that. They're hitting the wall or they're hitting each other, so it's going to make it more condensed. Here's what you're going to start to put down there with it. Strong intermolecular forces, guys. Typically solids are going to have the strongest. All right, they have high melting points and high boiling points. Okay. Strong intermolecular forces typically are solids are going to have the strongest. Again, high MPs and high BPs. It takes a lot of energy to get those to boil or to melt. What are some substances that you know from everyday life that have strong intermolecular forces? Metals, right? What did you say? Steel, right? They're ones, guys, they can withstand a lot because those forces holding those particles together, all right, they are stronger. What's another one that we've used in lab? You guys did a whole lab, your heating curve lab that you handed in last week. What did we use there? Water, right? Water, guys, it takes a while for water to boil. And the hungrier you are, it seems like the longer it takes, right? Because of a certain type of intermolecular force that we're going to talk about. Now, on the flip side, weaker ones are going to be gases. They have low melting points and low boiling points. Well, gases can't boil, but to get to the gas phase, right, boiling has to happen. So those substances that have weaker intermolecular forces will have lower boiling points. When we say, guys, they're gases or solids with these forces right here, we're talking about at room temperature. Okay, so at room temperature, strong intermolecular forces typically will be solids. Weak intermolecular forces will be gases. Things like nitrogen. We saw it last week with the dry ice. Solid carbon dioxide. It went from the solid to gas phase right away. What is that known as? Sublimation. But at room temperature, it was a gas because of those weak intermolecular forces. Right? Can I go on? So, 3 types. Don't write anything down for these yet. We're just introducing the 3 types. We're going to get into them in more detail in just a minute, so you don't need to write anything down. Dispersion forces, guys, sometimes they are called London dispersion forces, you will see. Dipole forces. And then hydrogen bonds. So these are the 3 that you need to be aware of, and you will be asked questions on your Regents exam about. Dispersion are the weakest. Dipole are in the middle, and then the strongest are going to be hydrogen bonds. We're going to get into these a lot more in just a second, so hold tight, don't write anything down just yet. We'll look at them individually. The first one, dispersion forces. They are instantaneous and momentary, all right, which means they fluctuate. They result from motions of electrons. So what this figure here, guys, is showing you, you can write this stuff down now because it's talking about those dispersion forces. If the charge cloud is not symmetrical, it will induce an asymmetry in its neighbor's charge cloud. All right, so that's what I want you to write down there for London dispersion forces in that space provided. Okay, so I want you to add that, guys. Every single substance has these London dispersion forces. So that's a term. You'll either hear them called dispersion or London dispersion. Every substance has those because, again, they're temporary. They're fluctuating because the electrons within a cloud on a molecule or an atom are moving. And that can create what we call a temporary dipole. Break that term down, guys. Dipole. What does that mean? Di means two, right? So you have two poles. What's a pole? Like, think about magnets. Right, you've got two charges. You got a positive and negative end, okay? So you've got two charges that are very momentarily created. And that's where that attraction comes from. This is why these are the weakest, is because they are very momentary. They're fleeting. Okay? They're not going to stay there all the time. So this is sigma plus and sigma minus. They're temporary. They're slight positive, slight negative charges, but they're changing all the time. All right? That's why they're the weakest. So if there's anything you take from this, guys, they're weakest because they're not permanent. They're very temporary. All right? So these are nonpolar molecules that we're talking about. So nonpolar, guys, which means no poles, they can't tell one end of the molecule from the other. That means they're symmetrical. So these dispersion forces, guys, come from nonpolar ones, but then they very quickly will shift because of electrons moving around and become temporarily charged. Okay? So some nonpolar molecules. All your noble gases, guys. All the noble gases. Why? Because they have a stable what? Stable valence electron shell, okay? Diatomics, where both atoms are the same. I'm just giving you some examples. You don't have to jot this all down, okay? But just think about it, guys. Your noble gases, they're going to be nonpolar. Diatomics, we've already talked about it. They're nonpolar. Large organic molecules, we'll talk more about those later on in the year. You don't have to write them all down just yet. Yes?
So this picture of the two green circles,
yep.
The same thing with different names.
When we talk about forces and size, there's one big thing, guys, that I want you to remember. So we're going to try keep it simple, and when we get to the end of talking about these forces, I'm going to summarize the big things you want to keep in your brain from each type of force, okay? Dispersion forces increase with the size of the molecule. So there's your first bullet point. The larger the electron cloud, the greater fluctuations of charge can be, okay? Think about it. The more electrons you have, the more potential there is for moving those electrons around, creating a charge. So, for example, if we look at those substances that we just talked about, the noble gases. The larger the noble gas, the greater the forces are. Same thing with the diatomics, part of Brinkelhoff. All right, now these are the halogens here that it gives you for an example. And there's an interesting piece, guys, with these. If you were to look on some periodic tables, I don't think ours shows it, but there are some where the symbols show you what they are. They're color coordinated to show you what their states of matter are at room temperature. All right. Most of the nonmetals are gases, but there's two liquids on the periodic table at room temperature. Bromine is one of those. So this is actually a gas, a liquid, and a solid. So that has some impact going along with the size. The bigger they are, it should make sense that, hey, if those forces are going to be stronger, their properties are going to change. Their substance is going to change. Their state of matter will change, all right, at room temperature. So that kind of explains, or hopefully explains, why iodine at room temperature is a solid, bromine's a liquid, the other two are gases, because those forces, those intermolecular forces are stronger, because their size is bigger. That's the big thing you got to remember here with this. The bigger the molecule with dispersion forces, the stronger those forces are going to be. Now, we haven't been able to use liquid nitrogen in the classroom. I can't get it. But it starts to boil at such a low temperature because it has very, very weak intermolecular forces. All right? When we bring it down to room temperature, it's constantly boiling. It's going from that liquid to solid state because those forces holding it together are very weak. So those particles can just spread out like crazy. All right? Very, very weak ones. So, these are the couple bullet points, guys, that you have there underneath dipole forces. So, polar molecules. All right, what's a polar molecule? It has poles, right? A positive and a negative piece. Greater polarity, guys, stronger force of attraction. That's one bullet point you need to jot down there for polar molecules. We're going to talk about hydrogen bonding in just a second. That's the third force. Now we're getting into dipole-dipole forces. So these dipole-dipole interactions happen with polar molecules because you have a permanent pole. So the examples that I have here is hydrogen chloride. Right? Notice by just the size of them. We looked at this back in bonding in Unit 4. Chlorine is very, very electronegative. It's going to pull those electrons away from hydrogen. Hydrogen wants to give them away to become stable. All right? So chlorine is going to, there's an unequal sharing that's happening. Chlorine is going to take those in more and be more aggressive. All right? That creates a permanent pole. The ones we just talked about were temporary. They were there, then they weren't there. They're fluctuating back and forth. These ones are not fluctuating. They are permanent. They stay. So it gives them different forces. It makes them stronger than dispersion ones because they're always there. So we're looking at the sharing of electrons. Now remember, does anybody remember back to Unit 4, we looked at differences in electronegativity. So Table S in your reference packet. Get those out. Biggest thing, guys, you want to remember about the charge with polar molecules, opposites are going to attract. It's permanent. So some examples that you have there, I list them underneath or next to where it says polar. Okay. They're going to attract. So this is not something that's fleeting, which again makes those intermolecular forces stronger because it's always there. You have that unequal distribution of electrons, one's pulling harder than the other. Yes, Grant? So the last of the three forces, like I said, we're going to summarize these in minutes. If you're confused, guys, I'm throwing a lot at you, breathe easy. It's going to be okay. Hydrogen bonding, guys, remember what I told you? Remember, what are the three most electronegative elements on the periodic table? Chem is? Fond. This is why I try to get you guys to remember. Because hydrogen bonding, guys, only occurs if you have fluorine, oxygen, or nitrogen in a compound. Chem is fond, those three most electronegative ones. So it occurs between molecules containing HF, HO, or HN bonds. This is the extreme case of dipole-dipole. So really, guys, even though we call it hydrogen bonding like it's its own thing, it's a subset of dipole-dipole bonding. Okay? Because these ones really attract those electrons. They're the most electronegative. They are aggressive in bringing in electrons, which we talked about back in Unit 4. Note to self, the H end is always going to be positive, so therefore the F, the O, or the N is where your negative piece comes in. And that's what this picture shows. And I know you don't have it in your notes, so maybe you want to just draw a molecule of water in there, like so. Okay? Something like this. And have your slightly negative, slightly positive, and that's why water gets its shape the way it is. This is why ice floats, guys, because you have these strong hydrogen bonding forces. Now that's something the name is kind of a little misnomer or disclaimer there. It's not actual bonding, right? There's not a share of electrons or a transfer of electrons. It's an intermolecular force. Okay, so it's an interaction between particles. It's not really electrons being transferred. Okay, and notice how you have in this picture there's a dotted line between them. That kind of indicates, hey, some of those intermolecular forces are taking place. But guys, this is why ice floats, because what happens is when water molecules are together in liquid, they're flowing freely. But when they solidify, they get into a very rigid shape because of the hydrogen bonding that's taking place. You've got this negative oxygen end being attracted to the hydrogen one, so it creates some empty space between them. This is why ice, solid water, is less dense than liquid water because you have empty space in between the molecules that makes it less dense. It makes it a little bit bigger volume than what you have. This is why water expands, why you shouldn't, has anybody ever had a brand new bottle of water they put in the freezer to get cold really fast? Maybe you left it in there too long and it freezes. What happens to that bottle? It expands, right? Sometimes you notice like the bottom of it kind of pushes out the bottom because the ice gets bigger. It's got a bigger volume because of the hydrogen bonds that are there within it. Big thing you got to remember, guys, is bond. Hydrogen bonding only occurs with F, O, and N within those molecules. All right, so you don't have to write this down. We just talked about it. Oxygen, guys, is going to be the negative end. The hydrogen is always the positive. So really what you want to remember, guys, where you see hydrogen, it's going to be the positive end. All right? That's what we just talked about. I'm going to kind of skip over that. So what we can look, guys, what we can see here is that if we have a graph, you don't have to write this down. This is not there for you. Hydrogen bonding, guys, gives it certain properties. Take a look at the vapor pressure diagrams in your reference table. So we started talking last week about vapor pressure. Table H. Table H. Right there. It's their last bullet point under hydrogen bonding. Increased boiling point over predicted value based on molecular size and comparison, guys. So it's an increased boiling point. Why? It's the strongest intermolecular force. Okay? Those are kind of the definitions of those. Now we're going to kind of just summarize, guys. We're not done yet. We're just going to summarize the strength of those. So here we go. The more electronegativity, guys, the stronger it is. So fluorine, in that order, F-O-N. That's why it's chemist bond. F-O-N. All right? Fluorine is going to be the strongest of hydrogen bonding. Nitrogen would be the weakest of hydrogen bonding. So make sure you get this into your notes. This is in decreasing order, guys. Ionic bonds. Now these are, we're going to make this, remember, okay? Ionic bonds and covalent bonds, these are the intra forces, and these last three are the inter. But we're kind of putting them on a scale comparing them to one another, guys. Ionic bonds are the strongest things. Why? Because what's happening with their electrons? Review. What's going on with ionic bonds? Transfer. Covalent is sharing. Now those are the only two that are talking about moving electrons within those particles. The last three here, guys, hydrogen bonds, dipole-dipole, and London dispersion, those are between molecules. So they're after the molecules are already formed. Okay? So hydrogen bond is the strongest for intermolecular forces, and going down to dispersions.